Chapter 12, Part 5 of Volume 2 of Airplane Flying Handbook, FAA-H-8083-3A. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Recording by Steve Vito, www.stevevito.com. Airplane Flying Handbook by the FAA. Chapter 12, Engine Inoperative Loss of Directional Control Demonstration. An engine inoperative loss of directional control demonstration, often referred to as a VMC demonstration, is a required task on the practical tests for a multi-engine class rating. A thorough knowledge of the factors that affect VMC, as well as its definition, is essential for multi-engine pilots, and as such, an essential part of that required task. VMC is a speed established by the manufacturer, published in the AFM-POH, and marked on most airspeed indicators with a red radial line. The multi-engine pilot must understand that VMC is not a fixed airspeed under all conditions. VMC is a fixed airspeed only for the very specific set of circumstances under which it was determined during aircraft certification. See Figure 12-19. In reality, VMC varies with a variety of factors as outlined below. The VMC noted in practice and demonstration, or in actual single-engine operation, could be less or even greater than the published value, depending upon conditions and technique. In aircraft certification, VMC is the sea-level calibrated airspeed, at which, when the critical engine is suddenly made inoperative, it is possible to maintain control of the airplane with that engine still inoperative, and then maintain straight flight at the same speed with an angle of bank of not more than 5 degrees. The foregoing refers to the determination of VMC under dynamic conditions. This technique is only used by highly experienced flight test pilots during aircraft certification. It is never to be attempted outside of these circumstances. In aircraft certification, there is also a determination of VMC under static or steady-state conditions. If there is a difference between the dynamic and static speeds, the higher of the two is published as VMC. The static determination is simply the ability to maintain straight flight at VMC with a bank angle of not more than 5 degrees. This more closely resembles the VMC demonstration required in the practical tests for a multi-engine class rating. The AFM-POH published VMC is determined with the critical engine inoperative. The critical engine is the engine whose failure has the most adverse effect on directional control. On twins with each engine rotating in conventional clockwise rotation as viewed from the pilot's seat, the critical engine will be the left engine. Multi-engine airplanes are subject to the P factor, just as single-engine airplanes are. The descending propeller blade of each engine will produce greater thrust than the ascending blade when the airplane is operated under power and at positive angles of attack. The descending propeller blade of the right engine is also a greater distance from the center of gravity, and therefore has a longer moment arm than the descending propeller blade of the left engine. As a result, failure of the left engine will result in the most asymmetrical thrust, adverse yaw, as the right engine will be providing the remaining thrust. See Figure 12-19. Many twins are designed with a counter-rotating right engine. With this design, the degree of asymmetrical thrust is the same with either engine inoperative. No engine is more critical than the other, and a VMC demonstration may be performed with either engine windmilling. In aircraft certification, dynamic VMC is determined under the following conditions. Maximum available takeoff power. VMC increases as power is increased on the operating engine. With normally aspirated engines, VMC is highest at takeoff power and sea level, and decreases with altitude. With turbocharged engines, takeoff power, and therefore VMC, remains constant with increases in altitude up to the engine's critical altitude, the altitude where the engine can no longer maintain 100% power. Above the critical altitude, VMC decreases just as it would with a normally aspirated engine, whose critical altitude is sea level. VMC tests are conducted at a variety of altitudes. The results of those tests are then extrapolated to a single sea level value. Windmilling propeller. VMC increases with increased drag on the inoperative engine. VMC is highest, therefore, when the critical engine propeller is windmilling at a low pitch, high RPM blade angle. VMC is determined with the critical engine propeller windmilling in the takeoff position, unless the engine is equipped with an auto feather system. Most unfavorable weight and center of gravity position. VMC increases as the center of gravity is moved aft. The moment arm of the rudder is reduced, and therefore its effectivity is reduced as the center of gravity is moved aft. At the same time, the moment arm of the propeller blade is increased, aggravating asymmetrical thrust. Invariably, the aftmost CG limit is the most unfavorable CG position. Currently, 14 CFR Part 23 calls for VMC to be determined at the most unfavorable weight. For twin certification under CAR 3 or early 14 CFR Part 23, the weight at which VMC was determined was not specified. VMC increases as weight is reduced. See Figure 12-20. Landing gear retracted. VMC increases when the landing gear is retracted. Extending landing gear aids directional stability, which tends to decrease VMC. Wing flaps in the takeoff position. For most twins, this will be 0 degrees of flaps. Cowl flaps in the takeoff position. Airplane trimmed for takeoff. Airplane airborne and ground effect negligible. Maximum of 5-degree angle of bank. VMC is highly sensitive to bank angle. To prevent claims of an unrealistically low VMC speed in aircraft certification, the manufacturer is permitted to use a maximum of a 5-degree bank angle toward the operative engine. The horizontal component of lift generated by the bank assists the rudder in counteracting the asymmetrical thrust of the operative engine. The bank angle works in the manufacturer's favor in lowering VMC. VMC is reduced significantly with increases in bank angle. Conversely, VMC increases significantly with decreases in bank angle. Tests have shown that VMC may increase more than 3 knots for each degree of bank angle less than 5 degrees. Loss of directional control may be experienced at speeds almost 20 knots above published VMC when the wings are held level. The 5-degree bank angle maximum is a regulatory limit imposed upon manufacturers in aircraft certification. The 5-degree bank angle does not inherently establish zero side slip or best single-engine climb performance. Zero side slip, and therefore best single-engine climb performance, occurs at bank angles significantly less than 5 degrees. The determination of VMC in certification is solely concerned with the minimum speed for directional control under a very specific set of circumstances, and has nothing to do with climb performance, nor is it the optimum airplane attitude or configuration for climb performance. During dynamic VMC determination in aircraft certification, cuts of the critical engine using the mixture control are performed by flight test pilots while gradually reducing the speed with each attempt. VMC is the minimum speed at which directional control could be maintained within 20 degrees of the original entry heading when a cut of the critical engine was made. During such tests, the climb angle with both engines operating was high, and the pitch attitude following the engine cut had to be quickly lowered to regain the initial speed. Pilots should never attempt to demonstrate VMC with an engine cut from high power, and never intentionally fail an engine at speeds less than VSSE. The actual demonstration of VMC and recovery in flight training more closely resembles static VMC determination in aircraft certification. For a demonstration, the pilot should select an altitude that will allow completion of the maneuver at least 3,000 feet AGL. The following description assumes a twin with non-counter rotating engines, where the left engine is critical. With the landing gear retracted and the flaps set to the takeoff position, the airplane should be slowed to approximately 10 knots above VSSE or VYSE, whichever is higher, and trimmed for takeoff. For the remainder of the maneuver, the trim setting should not be altered. An entry heading should be selected and high RPM set on both propeller controls. Power on the left engine should be throttled back to idle as the right engine power is advanced to the takeoff setting. The landing gear warning horn will sound as long as the throttle is retarded. The pilot should continue to carefully listen, however, for the stall warning horn, if so equipped, or watch for the stall warning light. The left yawing and rolling movement of the asymmetrical thrust is counteracted primarily with the right rudder. A bank angle of 5 degrees, a right bank in this case, should also be established. While maintaining entry heading, the pitch attitude is slowly increased to decelerate at a rate of 1 knot per second, no faster. As the airplane slows and control effectivity decays, the increasing yawing tendency should be counteracted with additional rudder pressure. Aileron displacement will also increase in order to maintain 5 degrees of bank. An airspeed is soon reached where full right rudder travel and a 5-degree right bank can no longer counteract the asymmetrical thrust, and the airplane will begin to yaw uncontrollably to the left. The moment the pilot first recognizes the uncontrollable yaw, or experiences any symptom associated with a stall, the operating engine throttle should be sufficiently retarded to stop the yaw as the pitch attitude is decreased. Recovery is made with a minimum loss of altitude to straight flight on the entry heading at VSSE or VYSE before setting symmetrical power. The recovery should not be attempted by increasing power on the windmilling engine alone. To keep the foregoing description simple, there were several important background details that were not covered. The rudder pressure during the demonstration can be quite high. In certification, 150 pounds of force is permitted before the limiting factor becomes rudder pressure, not rudder travel. Most twins will run out of rudder travel long before 150 pounds of pressure is required. Still, it will seem considerable. Maintaining altitude is not a criterion in accomplishing this maneuver. This is a demonstration of controllability, not performance. Many airplanes will lose or gain altitude during the demonstration. Begin the maneuver at an altitude sufficient to allow completion by 3,000 feet AGL. As discussed earlier, with normally aspirated engines, VMC decreases with altitude. Stalling speed, VS, however, remains the same. Except for a few models, published VMC is almost always higher than VS. At sea level, there is usually a margin of several knots between VMC and VS, but the margin decreases with altitude, and at some altitude, VMC and VS are the same. See Figure 12-21. Should a stall occur while the airplane is under asymmetrical power, particularly high asymmetrical power, a spin entry is likely. The yawing moment induced from asymmetrical thrust is little different from that induced by full rudder in an intentional spin in the appropriate model of a single-engine airplane. In this case, however, the airplane will depart controlled flight in the direction of the idle engine, not in the direction of the applied rudder. Twins are not required to demonstrate recoveries from spins, and their spin recovery characteristics are generally very poor. Where VS is encountered at or before VMC, the departure from controlled flight may be quite sudden, with strong yawing and rolling tendencies to the inverted position, and a spin entry. Therefore, during a VMC demonstration, if there are any symptoms of an impending stall, such as a stall warning light or horn, airframe or elevator buffet, or rapid decay in control effectiveness, the maneuver should be terminated immediately, the angle of attack reduced as the throttle is retarded, and the airplane returned to the entry airspeed. It should be noted that if the pilots are wearing headsets, the sound of a stall warning horn will tend to be masked. The VMC demonstration only shows the earliest onset of a loss of directional control. It is not a loss of control of the airplane when performed in accordance with the foregoing procedures. A stalled condition should never be allowed to develop. Stalls should never be performed with asymmetrical thrust, and the VMC demonstration should never be allowed to degrade into a single-engine stall. A VMC demonstration that is allowed to degrade into a single-engine stall with high asymmetrical thrust is very likely to result in the loss of control of the airplane. An actual demonstration of VMC may not be possible under certain conditions of density altitude or with airplanes whose VMC is equal to or less than VS. Under those circumstances, as a training technique, a demonstration of VMC may be safely conducted by artificially limiting rudder travel to simulate maximum available rudder. Limiting rudder travel should be accomplished at a speed well above VS, approximately 20 knots. The rudder limiting technique avoids the hazard of spinning as a result of stalling with high asymmetrical power, yet is effective in demonstrating the loss of directional control. The VMC demonstration should never be performed from a high-pitch attitude with both engines operating and then reducing power on one engine. The preceding discussion should also give ample warning as to why engine failures are never to be performed at low airspeeds. An unfortunate number of airplanes and pilots have been lost from unwarranted simulated engine failures at low airspeeds that degenerated into loss of control of the airplane. VSSE is the minimum airspeed at which any engine failure should be simulated. Multi-engine training considerations. Flight training in a multi-engine airplane can be safely accomplished if both the instructor and the student are cognizant of the following factors. No flight should ever begin without a thorough pre-flight briefing of the objectives, maneuvers, expected student actions, and completion standards. A clear understanding must be reached as to how the simulated emergencies will be introduced and what action the student is expected to take. The introduction, practice, and testing of emergency procedures has always been a sensitive subject. Surprising a multi-engine student with an emergency without a thorough briefing beforehand has no place in flight training. Effective training must be carefully balanced with safety considerations. Simulated engine failures, for example, can very quickly become actual emergencies or lead to loss of the airplane when approached carelessly. Pulling circuit breakers can lead to a subsequent gear-up landing. Stall spin accidents in training for emergencies rival the number of stall spin accidents from actual emergencies. All normal, abnormal, and emergency procedures can and should be introduced and practiced in the airplane as it sits on the ground, power off. In this respect, the airplane is used as a cockpit procedures trainer, CPT, ground trainer, or simulator. The value of this training should never be underestimated. The engines do not have to be operating for real learning to occur. Upon completion of a training session, care should be taken to return items such as switches, valves, trim, fuel selectors, and circuit breakers to their normal positions. Pilots who do not use a checklist effectively will be at a significant disadvantage in multi-engine airplanes. Use of a checklist is essential to safe operation of airplanes, and no flight should ever be conducted without one. The manufacturer's checklist or an aftermarket checklist for the specific make, model, and model year should be used. If there is a procedural discrepancy between the checklist and AFMPOH, then the AFMPOH always takes precedence. Certain immediate action items, such as a response to an engine failure in a critical phase of flight, should be committed to memory. After they are accomplished, and as workload permits, the pilot should verify the action taken with a printed checklist. Simulated engine failures during the takeoff ground roll should be accomplished with the mixture control. The simulated failure should be introduced at a speed no greater than 50% of VMC. If the student does not react promptly by retarding both throttles, the instructor can always pull the other mixture. The FAA recommends that all in-flight simulated engine failures below 3,000 feet AGL be introduced with a smooth reduction of the throttle. Thus, the engine is kept running and is available for instant use if necessary. Throttle reduction should be smooth rather than abrupt to avoid abusing the engine and possibly causing damage. All in-flight engine failures must be conducted at VSSE or above. If the engines are equipped with dynamic crankshaft counterweights, it is essential to make throttle reductions for simulated failures smoothly. Other areas leading to dynamic counterweight damage include high RPM and low manifold pressure combinations, overboosting, and propeller feathering. Severe damage or repetitive abuse to counterweights will eventually lead to engine failure. Dynamic counterweights are found on larger, more complex engines. Instructors should check with the maintenance personnel or the engine manufacturer to determine if their engines are so equipped. When an instructor simulates an engine failure, the student should respond with the appropriate memory items and retard the propeller control towards the feather position. Assuming zero thrust will be set, the instructor should promptly move the propeller control forward and set the appropriate manifold pressure and RPM. It is vital that the student be kept informed of the instructor's intentions. At this point, the instructor may state words to the effect, "I have the right engine, you have the left. I have set zero thrust and the right engine is simulated feathered." There should never be any ambiguity as to who is operating what systems or controls. Following a simulated engine failure, the instructor should continue to care for the failed engine, just as a student cares for the operative engine. If zero thrust is set to simulate a feathered propeller, the cowl flap should be closed and the mixture leaned. An occasional clearing of the engine is also desirable. If possible, avoid high-power applications immediately following a prolonged cooldown at a zero-thrust power setting. The flight instructor must impress on the student multi-engine pilot the critical importance of feathering the propeller in a timely manner should an actual engine failure situation be encountered. A windmilling propeller, in many cases, has given the improperly trained multi-engine pilot the mistaken perception that the failed engine is still developing useful thrust, resulting in a psychological reluctance to feather, as feathering results in the cessation of propeller rotation. The flight instructor should spend ample time demonstrating the difference in the performance capabilities of the airplane with a simulated feather propeller, zero thrust, as opposed to a windmilling propeller. All actual propeller feathering should be performed at altitudes and positions where safe landings on established airports could be readily accomplished. Feathering and restart should be planned so as to be completed no lower than 3,000 feet AGL. At certain elevations, and with many popular multi-engine training airplanes, this may be above the single-engine service ceiling, and level flight will not be possible. Repeated feathering and unfeathering is hard on the engine and airframe, and should be done only as absolutely necessary to ensure adequate training. The FAA's practical test standards for a multi-engine class rating requires the feathering and unfeathering of one propeller during flight in airplanes in which it is safe to do so. While much of this chapter has been devoted to the unique flight characteristics of the multi-engine airplane with one engine inoperative, the modern well-maintained reciprocating engine is remarkably reliable. Simulated engine failures at extremely low altitudes, such as immediately after liftoff and or below VSSE, are undesirable in view of the non-existent safety margins involved. The high risk of simulating an engine failure below 200 feet AGL does not warrant practicing such maneuvers. For training in maneuvers that would be hazardous in flight, or for initial and recurrent qualification in an advanced multi-engine airplane, a simulator training center or manufacturer's training course should be given consideration. Comprehensive training manuals and classroom instruction are available along with system training aids, audio visuals, and flight training devices and simulators. Training under a wide variety of environmental and aircraft conditions is available through simulation. Emergency procedures that would be either dangerous or impossible to accomplish in an airplane can be done safely and effectively in a flight training device or simulator. The flight training device or simulator need not necessarily duplicate the specific make and model of an airplane to be useful. Highly effective instruction can be obtained in training devices for other makes and models, as well as generic training devices. The majority of multi-engine training is conducted in 4 to 6 place airplanes at weights significantly less than maximum. Single-engine performance, particularly at low-density altitudes, may be deceptively good. To experience the performance expected at higher weights, altitudes, and temperatures, the instructor should occasionally artificially limit the amount of manifold pressure available on the operative engine. Airport operations above the single-engine ceiling can also be simulated in this manner. Loading the airplane with passengers to practice emergencies at maximum takeoff weight is not appropriate. The use of the touch-and-go landing and takeoff in flight training has always been somewhat controversial. The value of the learning experience must be weighted against the hazards of reconfiguring the airplane for takeoff in an extremely limited time, as well as the loss of the follow-through ordinarily experienced in a full-stop landing. Touch and goes are not recommended during initial aircraft familiarization in multi-engine airplanes. If touch and goes are to be performed at all, the student and instructor responsibilities need to be carefully briefed prior to each flight. Following touchdown, the student will ordinarily maintain directional control while keeping the left hand on the yoke and the right hand on the throttles. The instructor resets the flaps and trim and announces when the airplane has been reconfigured. The multi-engine airplane needs considerably more runway to perform a touch and go than a single-engine airplane. A full-stop taxiback landing is preferable during initial familiarization. Solo touch and goes in twins are strongly discouraged. End of Chapter 12. This has been read by Steve Vito, www.stevevito.com.